Pick a moment from yesterday that stung you. A short word from someone you love. A worry you carried home from work. An embarrassment that played itself back in your head at 3 in the afternoon and would not stop. Now sit still for a second and feel where that memory lives in you this morning. The story is still there. The sting is duller. I want to tell you exactly what happened to that feeling while you were asleep. It was a chemical event in your brainstem. It lasted about 22 minutes. It happened in the last hour before your alarm went off. And it was as precise as a reaction in a beaker, and as physical as a thunderstorm. Now look, I want to start by giving you a tour of the place where this happens, because most of us go through life without ever locating the parts of ourselves that do the most important work. Find the spot at the very base of your skull, where the bone meets the muscle of your neck. Press there gently with your thumb. Just under that pressure, inside the bone, sits a structure called the brainstem. It is the oldest part of you. It is the part you share with the lizard and the fish. In the upper portion of that brainstem, in a region called the pons, there are 2 tiny clusters of cells. Each cluster is no bigger than a grain of rice. There are about 15,000 cells in each one. Together they are called the locus coeruleus. The Latin means the blue spot. If you slice the brainstem of a fresh specimen, you would see them as 2 specks of blue on the tissue. The color comes from a pigment that builds up inside the cells themselves over a lifetime. These 2 grains of rice are the alarm system of your entire brain. Every time you are startled, every time you focus, every time you panic, the locus coeruleus fires. It releases a molecule called noradrenaline. That molecule travels along thin nerve fibers, branching like the roots of a tree, to almost every other part of your brain. It is the chemical message that says, "Pay attention, this matters, stay alert." Without it, you would not be awake. You would not be able to focus. You would not be able to feel afraid when fear is the appropriate response. Now move your fingers up from your neck. Place them on your temples, just behind the eyes, and imagine pressing inward, deeper than where your fingers can reach. About 2 inches inside your skull, on each side there is a structure shaped like an almond. The Greek word for almond is amygdala. There are 2 of them, one in each temporal lobe, each about the size of a sugar cube. The amygdala is your salience detector. When something happens that matters, a face you should fear, a voice you should trust, a touch you should remember, the amygdala fires and tags the experience as important. Without it, you would still see, you would still hear, but nothing would feel like anything. A little behind and below each amygdala, curling like a seahorse around the inside of each temporal lobe, sits the hippocampus. The Greek word for seahorse is hippocampus. This structure is your librarian. Memories pass through it on their way to long-term storage. And finally, behind your forehead, just above the eyes, sits a sheet of cortex called the medial prefrontal cortex. This is the part of you that thinks before it speaks. The part that overrides the amygdala when the amygdala wants to scream and the situation does not call for screaming. These 4 structures, locus coeruleus, amygdala, hippocampus, medial prefrontal cortex, are wired together. The wires run in both directions. They talk to each other constantly. When you are awake, that conversation is loud. When you are in deep sleep, the conversation goes quiet but does not stop. And when you enter REM sleep, something happens to the locus coeruleus that does not happen anywhere else in your 24-hour day. It goes silent. Now let me sketch the shape of your night, because you cannot see what the silencing is doing until you understand where in the night it does it. You go to bed. You drift. Within about 10 minutes you enter a stage called N1, light sleep. You drop into N2, then into N3, the deep slow wave sleep where the body does its physical repair. About 90 minutes after you fell asleep, you enter your first bout of REM sleep. REM stands for rapid eye movement. Your eyes flicker behind closed lids. Your muscles go limp. Your brain begins to dream. That first REM bout is short, maybe 10 minutes. Then you slide back down through the non-REM stages, and the cycle starts again. Here is the part most people do not know. The cycles are not equal. In the first 90-minute cycle of the night, you spend most of your time in deep, slow-wave sleep, and only a small slice in REM. In the second cycle, the proportions begin to shift. By the third cycle, REM has gotten longer. By the fourth, longer still. By the fifth, your REM bout can stretch to 20, 25, even 30 minutes. The average length of the final REM period in a normal 8-hour night is right around 22 minutes. Mary Carskadon and William Dement at Stanford mapped this architecture in detail starting in the 1970s. They put electrodes on the scalps of hundreds of sleepers and recorded their brains all night. The pattern is consistent across humans. The pattern is consistent across mammals. The progressive lengthening of REM is not random. It is engineered. I want you to think about what this means for your life. If you sleep 6 hours instead of 8, you do not lose a quarter of your sleep evenly across the stages. You lose almost the entire final cycle. You lose the longest REM bout. You lose the bout where the most emotional processing happens. Cutting 2 hours off the end of your night can remove 40 to 50% of your total REM sleep, even though you are only losing a quarter of your time in bed. The alarm clock is not a neutral device. It is a guillotine, and it falls on the most chemically important minutes of your night. But the duration alone does not explain why these particular minutes matter so much. After all, you have been asleep for hours by the time the long REM bouts arrive. The answer lies in the chemistry. And the chemistry begins with that pair of grains of rice in your brainstem going completely quiet. Imagine a streetlight that has been on continuously for 16 hours. That is your locus coeruleus during the day. It fires at a steady tonic rate, releasing noradrenaline into your forebrain like a constant low hum. The hum is what makes you you. It holds your attention together. It lets you respond to a sudden noise. It is the chemical foundation of vigilance. When you fall asleep, the streetlight begins to flicker. In 1981, Gary Aston Jones and Floyd Bloom at the Salk Institute were among the first to record locus coeruleus neurons across the sleep-wake cycle. They placed fine electrodes inside the brainstem of cats and watched the cells fire. During waking, the cells fired about 3 times per second. During non-REM sleep, the rate dropped to about 1 per second. Then, when REM sleep began, the cells stopped firing entirely. Not slower, not quieter. Stopped. For the duration of REM sleep, the locus coeruleus is silent. This is the only time in your 24-hour day that this happens. You can be in deep meditation and the cells still fire. You can be sedated and the cells still fire. The only known state in which the locus coeruleus completely shuts off is REM sleep. The consequence is that noradrenaline levels in your forebrain, the front part of your brain where thought and feeling and decision live, drop to near zero. The chemical of alarm is gone. The brain enters a neurochemical state it cannot enter any other way. Anita Luti at the University of Lausanne, with her colleagues Georgios Foustukos and Alejandro Osorio Forero, published a paper in Nature Neuroscience in 2024, showing exactly when the locus coeruleus permits the door to REM to open. During non-REM sleep, the locus coeruleus pulses on a slow cycle, about every 50 seconds. It surges, then quiets, then surges again. The brain can only enter REM during one of those quiet troughs. Luthi called the locus coeruleus the gatekeeper of the sleep cycle, and the metaphor is precise. The structure is literally controlling when the door to REM can open. Once that door opens, the locus coeruleus does not just dip. It silences. Now I want you to understand what this state is like, chemically. In waking, your brain is a soup of monoamines, noradrenaline, serotonin, dopamine, histamine, all of them signaling, all of them telling the cortex how to weight what it is processing. In REM sleep, almost all of these are suppressed. Acetylcholine is high. The cortex is active, the eyes are moving, the brain is dreaming. But the alarm chemistry is gone. Imagine watching a horror film with the sound turned off. The images still flicker on the screen. The actors still act. The plot still unfolds. But the strings are not screaming, and the bass is not pounding, and the audio that tells your nervous system to be afraid is simply not playing. The visual content is intact. The emotional pressure has been removed. That is what your brain is doing during REM sleep. It is replaying yesterday. It is rerunning the moment your boss looked at you a certain way, the moment your child said something that hurt, the worry about the bill, the embarrassment from the meeting that morning. The amygdala is firing. The hippocampus is firing. The visual cortex is generating images. But the soundtrack of stress is muted because the locus coeruleus has stopped speaking. This is why dreams can feel so vivid and yet so emotionally strange. The content is there. The chemistry that would normally accompany the content is not. While the locus coeruleus is silent, something underneath is doing the actual work. The amygdala is not merely replaying yesterday's memories. It is being rewired in real time. In 2007, a team led by Sung-Shik Yu, working in Matthew Walker's laboratory at the University of California, Berkeley, ran a study that I think every adult should know about. They took two groups of healthy people. One group slept normally. The other group was kept awake for 36 hours. Then they put both groups in a brain scanner and showed them images. Some of the images were neutral. Some were progressively more disturbing, the kind of images that make any nervous system flinch. The amygdala of the rested group lit up in response to the disturbing images. That was expected. The amygdala is supposed to flinch. The amygdala of the sleep-deprived group lit up 60% more. 60%. Not slightly more. More than half again as much, in the same brains, looking at the same images, after just one missed night. And inside that first finding was a second finding. In the rested group, the amygdala was talking to the medial prefrontal cortex. That conversation is what regulates emotion in waking life. The prefrontal cortex says to the amygdala, "Yes, I see, but we do not need to scream right now." In the sleep-deprived group, that conversation had broken down. The amygdala was firing, and the prefrontal cortex was no longer connected to it. The brain was reactive without being regulated. Walker, working with his student Els van der Helm, proposed a model for what REM sleep is doing to prevent exactly this. They called it sleep to forget, sleep to remember. Here is what they meant. During REM sleep, the amygdala fires hard. Brain imaging studies have shown the amygdala can be up to 30% more active during REM than during waking. It is not resting. It is reactivating yesterday's emotional events. But it does this in a brain with no noradrenaline. So the memory content gets replayed and consolidated. The librarian, the hippocampus, files it into long-term cortical storage. That is the remember part. The episode is preserved. You will know tomorrow what happened today. But the emotional alarm attached to the memory is not getting reinforced because the chemistry of alarm is absent. The amygdala is firing into a chemical environment that does not lay down a stress signature. That is the forget part, not the memory. The intensity. By morning, the memory is filed. The emotional charge has dissipated. In 2011, van der Helm and her colleagues, including Justin Yao, Shubir Dutt, and Jared Salatin, published a paper in Current Biology titled REM Sleep Depotentiates Amygdala Activity to Previous Emotional Experiences. They showed that the overnight calming of the amygdala is directly correlated with the brainwave signature of clean REM sleep. The more REM you got with low gamma activity, gamma being the high-frequency oscillation that signals residual arousal, the more your amygdala calmed down between yesterday and today. In other words, the quality of your last REM bout predicts how much of yesterday's emotion is still gripping you when you wake up. The mechanism is real. The mechanism is measurable. And the mechanism is the difference between waking up able to face the day and waking up dragged backward into yesterday's worry. Now I want to show you what happens when this mechanism does not work, because that is where sleep neuroscience meets psychiatry, and where the stakes for you sitting there listening to me become very clear. In major depression, the architecture of sleep is distorted in characteristic ways. REM sleep starts too early, within 40 to 60 minutes of falling asleep, instead of the normal 90. There is more REM overall, but the REM is fragmented. The theta rhythm during REM, which normally holds steady at about 5 oscillations per second, becomes irregular. And, this is the key finding, the locus coeruleus does not fully silence during REM in depressed individuals. There is residual noradrenergic firing, which means the amygdala is replaying yesterday, but the dampening is incomplete. The emotional charge is not being unhooked from the memory. Each night, instead of softening yesterday's pain, the brain rehearses it with the alarm partially intact. Imagine running a clothes washer with no soap. The fabric goes around and around in the drum, but the dirt does not lift. That is what depressed REM looks like. In post-traumatic stress disorder, the failure is sharper. PTSD is associated with persistently elevated noradrenaline at baseline, and during REM the suppression often fails entirely. The brain tries to replay the trauma, but the locus coeruleus refuses to quiet. The replay happens with the alarm at full volume. The result is not depotentiation. The result is the consolidation of the trauma at full intensity. This is why people with PTSD often wake from nightmares in a panic state. The mechanism that should be unhooking the fear is instead reinforcing it. There is a class of evidence here that goes back to a drug called prazosin. Prazosin blocks alpha-1 adrenergic receptors, meaning it blocks the receivers of the noradrenaline signal. Murray Raskind, working with combat veterans at the Seattle Veterans Affairs Hospital in the early 2000s, found that prazosin reduces the frequency and intensity of trauma nightmares. When the body cannot silence the locus coeruleus naturally, blocking the receivers of its signal partially restores the mechanism. Not a cure, but meaningful. And the meaning tells us something. The silencing is not just a neat fact. It is a biological imperative. When it fails, mood disorders follow. When it succeeds, mood is regulated. I want you to think now of the person reading this who sleeps 6 hours a night and wakes feeling raw and irritable and reactive every morning. That person is not weak. That person is not lacking willpower. That person is being denied the final REM bout of every night. By the alarm clock, by the late screens, by the glass of wine that suppresses REM in the second half of the night, by the cup of coffee at 3 in the afternoon that lingers in the bloodstream past midnight, the 45-year-old who walks into work tense and short with her coworkers, who tries to be patient with her teenager and snaps anyway, who used to be steadier than this, the 55-year-old who finds himself crying at a song on the radio he has heard 1,000 times, the 65-year-old who lies awake at 3 in the morning with his eyes open, ruminating about a comment from his daughter last week. None of them are choosing this. Their brains have been deprived of the 22-minute window that would have done the emotional reset. The mechanism is starved. The mood follows. I have just told you a precise neurochemical story. Before I go further, I want to be honest with you about which parts of that story are settled, which parts are well supported but still being argued, and which parts are still being teased apart. What is settled? Beyond reasonable dispute. The locus coeruleus stops firing during REM sleep. This has been recorded directly in cats, in rodents, and indirectly in humans. The recordings have been replicated for over 4 decades. It is bedrock physiology. What is settled? Amygdala reactivity increases dramatically after sleep deprivation. The Ewan Walker finding has been replicated in different laboratories with different stimuli. The exact percentage varies. The direction of the effect does not. What is well supported but still being refined. The depotentiation model, that REM sleep specifically softens the emotional charge of yesterday's memories through the absence of noradrenaline, is supported by a great deal of brain imaging and brainwave data. Robert Stickgold at Harvard Medical School supports it. Walker supports it. Some researchers have proposed that slow-wave sleep also contributes meaningfully, and the precise division of labor between the stages is still being worked out. What is still being investigated? Whether the specific final 22-minute REM bout matters more than the cumulative effect of all the bouts together. The lengthening of REM through the night is real. The accumulation of emotional processing in the late night is real. But whether the special status comes from the duration, the cumulative count, or some specific physiological state of the late bouts, that is open. What is preliminary, but plausible? The clinical implications. We do not yet have a study that shows beyond doubt that protecting late REM in mildly depressed adults could substitute for medication. The mechanism is consistent with that hope. The clinical trials are not yet definitive. I tell you all this because I do not want you to come away thinking the science is finished. It is not. But the foundational claim that REM sleep, in a brain temporarily free of noradrenaline, performs an essential nightly emotional reset is as solid as any claim in modern neuroscience. The architecture is real. The chemistry is real. The mechanism is real. Now I want to talk about what happens when industry meets a free mechanism. Selective serotonin reuptake inhibitors. The class of antidepressants known as SSRIs. Fluoxetine, paroxetine, sertraline, citalopram, escitalopram. As of the most recent figures, roughly 1 in 8 American adults is taking one. The annual revenue worldwide is measured in tens of billions of dollars. Here is what INSRI does at the cellular level. It blocks the protein in the neuron membrane that pulls serotonin back out of the synapse after release. Serotonin lingers longer between neurons. Over several weeks, the brain recalibrates its serotonin and noradrenaline systems, and in many people this produces a measurable improvement in mood. Here is what INSRI also does, that you may not have heard. It powerfully suppresses REM sleep. Almost every SRI prolongs the latency before the first REM bout begins. It reduces the total time spent in REM. It often eliminates the longest late-night REM bouts entirely. Studies of paroxetine, vortioxetine, and fluoxetine all show significant REM suppression, often within days of starting treatment. This is the paradox I want you to sit with for a moment. The natural mechanism for emotional regulation requires REM. The pharmaceutical that improves mood suppresses REM. The reason it still works is downstream. The drug is hitting the same target chemistry from a different angle. The natural mechanism uses the silencing of the locus coeruleus during REM to allow the amygdala to be replayed without alarm. The SRI uses sustained serotonergic elevation, mediated through the serotonin 1A receptor, to indirectly dampen noradrenergic tone across both waking and sleeping. It bypasses the architectural elegance and brute forces the chemistry. It does work. For severe depression, for some people whose architecture is genuinely broken, it is life-saving. I am not telling you to stop taking your medication, but I want you to see what we have built. We have built a culture that systematically destroys the natural mechanism. Alcohol suppresses REM, often eliminating the second half of the night. Cannabis suppresses REM. Late-night light from screens suppresses melatonin and shortens REM. 6 hours sleep amputates the longest REM bout. Chronic stress and anxiety keep the locus coeruleus partially active during sleep, which prevents it from fully silencing during REM. Then, when the architecture has been starved across years and the mood begins to suffer, we medicate the consequence. The pharmaceutical costs about $30 a month for the generic, several hundred for the brand name version. It comes with sexual dysfunction in 50 to 70% of users. It comes with weight gain in many. It comes with emotional blunting in some. It comes with a notoriously difficult discontinuation syndrome. The mechanism in your brainstem costs nothing. It runs every night, free of charge. No prescription, no side effects, no insurance claim. It requires only the conditions in which it can run. It requires darkness. It requires enough hours. It requires a body that is not metabolizing alcohol or caffeine in the relevant window. It requires that the locus coeruleus be allowed to silence, which it cannot do if the body is in a state of chronic hypervigilance. I want to be careful here. I am not saying the natural mechanism replaces the drug. The dose difference is real. For severe depression, for bipolar illness, for clinical states where the architecture is fundamentally broken, the drugs are often necessary, and the lever the drug pulls is stronger and more direct. The pharmaceutical exists because some people genuinely cannot reach the natural mechanism on their own. But the millions of adults on antidepressants for mild and moderate complaints, who are simultaneously sleeping 6 hours, drinking wine in the evening, scrolling phones at midnight, and waking to alarms before their final REM bout completes, those people may be medicating the symptom of a starved mechanism. The drug is doing the work the architecture would have done for free if the architecture had been allowed to run. That is the asymmetry I want you to notice. Not because you should change anything tonight, because once you see it, you cannot unsee it. When my mother had something hard to decide, she would say, "Do not decide tonight. Wait until morning. The morning will know better than the evening." She did not know about the locus coeruleus. She had no brain imaging data. She did not know what happens to the amygdala in the absence of noradrenaline. But she had lived enough mornings after hard evenings to know that the same problem, looked at by the same brain, would be a different size after the brain had had its 22 minutes. She was right. Not in the soft way, in the chemical way. The morning brain is not the same brain as the evening brain. It is the evening brain minus the noradrenergic charge that was attached to yesterday's memories. Same content, less grip. The librarian has filed the events. The alarm has been disconnected from the file. So tonight, when you go to bed, do not think of sleep as the absence of waking. Think of it as a chemical procedure your brainstem is running on your behalf. Think of those final cycles before the alarm, the longest REM bout of the night, the one that does the heaviest emotional work, as the most important medical procedure you will receive all year, performed for free by a structure inside your skull that has been running it every night for as long as you have been alive. Protect that window. Give the locus coeruleus its silence. Let the amygdala replay yesterday in a brain, free of the alarm. Tomorrow's mood is being decided in there, right now, while you are listening to me. Tell me one thing that felt different this morning, that had been heavy last night. V.